Because, why is this class a treat? So if you're a math major, you take math 206, which is linear algebra, and you take math 242, which is differential equations. And if you're in this class, what you do is you smash those together into 242, and you can take both classes at the same time. 244. So you guys get 3/4 of 206 and 3/4 of 244 in 1/4. So it's like a class and a half in a class. So it's going to feel like this class is moving quick. And if you're going to complain, you don't complain to me, because I am not the gods of engineering who decided that this is. They trust you. They trust you so much that they trust that you can learn a class and a half inside the space of one class. So so this class, it's going to feel like it moves quickly. I will do my best to pad stuff out when I can. Almost all of us that teach this class, I think there's 2 left. Almost all of us that teach this class have to pick and choose the places where it's all going to seem kind of a little thin. There are going to be places where this class, there are going to be places that are thinner than others. I scare him out of the room. So there are going to be topics I have to miss. These are probably going to seem, at first blush, like they don't really go together. I will do my best to give it. I'm going to give a little introductory blurb today before we start talking about the math itself, to kind of show you where the idea of differential equations comes from, and sort of point to why we'd want to know the linear algebra component of it. Essentially, this class consists of the 2 most common languages for contemporary mathematics. Linear algebra and differential equations are what contemporary math and engineering mathematics are built out of. So they're not going to seem at the beginning like they go together, but they're sort of in interplay with each other. And I will do my best to I will force as many connections as I can. So to begin, the first thing you should probably be wondering is, okay, this class is called linear analysis, and I'm talking about something called differential equations. What the heck is that? So let's talk about what is differential equations. Okay, so to begin with, this isn't up on the webpage yet, but I'll post this one. This is just introductory. There's not really content in the first part of this that is necessary to take notes on if you don't want to. So we are well acquainted with things called algebraic equations, right? So an algebraic equation is an equation that involves algebraic operations: plus, minus, times, divide, and square root. Those are the algebraic operations. And so I could write an equation down like x squared plus 3x plus 2 is equal to 0. And you could find the solutions to that equation. Here, I've taken an unknown x, sort of an unknown number, x, and I've built an equation with algebraic operations involving x. And the idea is I would like to solve the equation. There's a pile of techniques that came along with that. You learned the quadratic equation, for example, or Descartes' rule of signs, or the rational root test, right? A whole pile of technique you guys learned to solve equations like this for the numbers that make the equations true. You also learned about trigonometric equations, probably with much less enthusiasm. So trigonometric equations are things like, sine of x is equal to cosine of x. Those are much harder to solve. Some of them can be solved, some of them can't be. But the idea here is you're still solving for numbers that make the equation true. So a trigonometric equation involves trig functions. You also learned about exponential equations. So you keep getting more sophisticated with the kind of equations we could write down. 2 to the x is equal to 10. The tools get more complicated, and not every equation can be solved perfectly. So especially if you start mixing things together, you can get equations that aren't solvable. 2 to the x plus x is equal to 10. You have no hope on that one. A computer needs to be used to solve that question. numerically. It has a solution. You could graph it and find out what that solution looks like, but you can't solve this using any tool except a computer numerically. So a differential equation, instead of involving an unknown that's a number, like all of these, starts with an unknown function. So a differential equation begins with an unknown function, y of x. And then we're going to build an equation that involves derivatives of y. Y prime prime plus y is equal to 0. That's a differential equation. I have an unknown function y, and I'm asking for what are the functions that satisfy this equation. As an example, here's a really easy one. How about y prime plus y, or if y prime is equal to y. So a solution to this equation would be figure out something to plug in for this unknown, a function that is equal to its own derivative. Which is? Okay, well 0, so that's really good actually. So y0 is definitely one, called the trivial solution. Not trivial because it's too easy, but that's just a way of indicating that it's the 0 solution. And then y is equal to e to the x. Now that's not all the solutions necessarily, but it's a solution, right? This function satisfies that equation. You can plug this in and it makes the equation true. So the solutions to differential equations are going to be functions. So the very first question you should have is, okay, so that's great. You can make up these operations. In fact, actually, before I go on to my motivation bit, I'm going to tell you, you've already solved a bunch of these. You may not have realized that you solved a bunch of these already, but every single time in your Calculus 142, which is before I had you, and you had an equation like the integral of x squared dx is equal to 1/3 x to the third plus c, you really were solving a differential equation when you took an antiderivative. You could rewrite this equation as, I would like to know, hey, I've got some function whose derivative is x squared. Find y. So every antiderivative, every indeterminate antiderivative like this, or indefinite antiderivative, was a differential equation. We just didn't tell you. Find the function whose derivative is x squared is what that tells you to do. Okay, so first obvious question, I got a bunch of you like to ask these, is like why, which is really secretly the question, who cares? Okay, so it turns out that many deeply important physical and mathematical processes are described most naturally by differential equations. So I'm going to begin with one. I didn't bring my prop today, which was supposed to be a hot cup of coffee. But imagine that I tell you that I would like to study the way that the temperature of my cup of coffee changes with respect to time. So I bring a hot cup of coffee in here, and I put it down on the table. And I ask you, okay, well, my coffee started here with initial temperature T naught. 200 degrees, say, if I got a really hot cup of coffee, or 200-degree cup of coffee. As time goes on, what happens to the cup of coffee?
It cools down.
It certainly gets cooler, but like if time goes for 6 hours, what is the temperature of the cup of coffee going to be?
The room temperature.
Pretty close to room temperature, right? So down here, imagine that you've got capital K, which is room temp. So I'm making up this graph. I'm thinking this is a time axis, and this is a temperature axis. So this is temperature, and this is time. So if you were going to guess at what the plot of this would be, well, I know that the cup of coffee can't go below room temperature, because otherwise I'd have a perpetual motion machine. That's illegal. So in the long run, it probably looks something like this, right? The coffee starts hot, and it cools down, and asymptotically it's going to approach room temperature. Now, we are making an assumption here, which is that the temperature of the room doesn't change in response to the coffee. There's really the room does warm slightly, but the room is so much bigger than the cup of coffee, we're just assuming that the temperature of the room doesn't change. Okay? So when I look at this graph, which is a reasonable interpretation of what should happen, I notice some qualities, right? First off, the object looks like it cools down pretty quickly initially, right? You got the, I don't know, probably not many of you guys drink coffee yet, but when you do start drinking coffee someday, you will discover that the first 5 minutes are really disappointing because you get this really awesome hot cup of coffee, and within 10 minutes it's lukewarm. And then, once it's lukewarm, it stays lukewarm for a long time before it gets down to room temperature. So it cools very quickly at first, but as more time goes on, and the closer it gets to this asymptote, the more slowly it cools. Well, I'm talking about rates of change, and that suggests maybe derivatives are involved, right? If I talk about how fast something is cooling, I'm talking about a rate of change of cooling. So Newton, the famous one, came up with something that he called, well, he probably didn't call it this, but we do, Newton's law of cooling. And Newton's law of cooling is a physical observation. It's not a mathematical statement yet. It's a physical observation. The rate of change of the temperature of an object is proportional to the difference between the temperature of the object and the surrounding temperature. Seems reasonable. The bigger the difference, the faster the cooling. Smaller the difference, the less the cooling. The closer the temperature of the object is to the ambient temperature, the less cooling happens. Slows down. If you're curious about the proportionality constant here, if you've done any sort of like study of materials in any of your classes so far, or you've taken your physics 2 and you learned about specific heat capacity, some things cool down very quickly and some things cool down very slowly, right? Some physical objects are very reluctant to cough up their heat. Water does not like to heat up and it does not like to cool down. Metal loves to heat up and cool down. So the rate at which this happens is also going to depend on the material, is why that extra constant is there. So what I'm going to do is I'm going to take this statement and I'm going to translate it into math. The rate of change of the temperature of an object, oh, I have a name for that. The temperature of the object, that was T. So the rate of change of the temperature of an object, that's the derivative of temperature with respect to time. This is right here. If you remember back to like, I don't know, 6th grade or whatever, that's an equal sign. And then proportional to the difference. Proportional is going to be a constant of proportionality, which I will call little c, to the difference between the difference of between the temperature of the object and the surrounding temperature. Well, the temperature of the object is capital T, and the surrounding temperature is the ambient temperature, which I called K. So all of the words in my physical observation correspond to terms of a mathematical equation. And if I wrote that down, I guess I'm going to be a little bit pedantic here. I'm going to make this minus C because I want the object to be cooling when it's warmer. So you can, I'm going to write a minus here to ensure that the C has a positive value because it makes the math easier to see what's happening. So if I took that equation and I wrote it out, it would say dt is equal to C times T minus K. Minus C. And that is a differential equation. The unknown, the function t of t right here, that is the function that makes this graph. So the unknown of that equation is the function that makes this picture. We could also write this in Newton notation by writing t prime is equal to c times t minus k. This class is like completely ambivalent about what you should use. It will sometimes use the derivative notation when it's convenient to do so, or the fractional notation, and sometimes the Newton notation. I will say that we actually have one more piece of information. I told you the initial temperature. So as well, I have the information that the temperature at time 0 is equal to T naught. The initial temperature of the problem was T naught. So this is called an initial value. if I have an extra piece of information. And what this is here for, if you remember back in your 142 classes or whatever your integral calculus, how people just would not stop banging on about how you had to have plus c's in your answers. There's an infinite family of functions that solve this problem, but there's only one that solves the problem for that particular initial value. So this particular initial value will let you figure out what the plus c must have been. I mean, I could have come in with really cold coffee, right? So if I came in with like some terrible, sometimes the coffee is like this hot, then it's already starting pretty close. That curve is different than this one, right? So that would be a different initial value, which would give you a different solution to the same cooling problem. All right, so let me actually write down what the solution to this looks like. We do not yet have the technique for this. I will make a poll later on how many of you have seen this. But, the solution is T of t is equal to k plus t naught minus k times e to the minus ct. And let's just take a gander at that thing for a second and decide, okay, I wrote down my physical law that I think holds. I translated that into a differential equation. I solved it using techniques that we'll learn in chapter 1.4. Does this behave like I think the graph should behave? Well, what's t? So first condition we should check is, does it actually meet the initial condition? What is t of 0? K plus t naught minus k times e to the 0, which is k plus t naught minus k, which is, okay, so it meets the initial condition. That's nice. Now what happens asymptotically, which is to say, what happens when time gets really large? If I took the limit as t goes to infinity of t, that's the limit as t goes to infinity of k plus t naught minus k times e to the minus ct, little t. What is that limit?
Okay.
Why?
Because like e to the negative t is...
This is t is going to infinity, e to the minus infinity is 0. Right? That term disappears to 0, which kills all of this, and what's left behind is k. So it has the right initial condition, it has the right asymptotic condition, and what it suggests is this particular model of cooling gives you exponential decay in the cooling. Okay, so there's a bunch of things I haven't told you here, but the upshot is what we're going to be studying is all three parts of this. Coming up with a reasonable description of some physical situation, writing down the differential equation that you get from that, and solving it, and then interpreting what the answers mean. Now in practice, many cases, this is not a solvable problem. In most cases, this is not solvable, and computers do this part. Computers take the differential equation and they tell you what the answers are numerically. Right? In the same way that there's all kinds of integrals that you just can't do, or there's all kinds of equations you just can't solve. A lot of differential equations have solutions, but you can never have them. You have to write them down in some sort of numerical form, or if you really want to see what's going on, you got to continue on and take Math 344, which is Linear Analysis 2, where we teach you all the good stuff. This stuff is good too, but the even better stuff is 344. So I will try to teach 344 at some point in the next couple of quarters. So if anybody has to continue, they can see that stuff too. Okay, so that's kind of what's going on here. We are going to be studying first with for the first thing we're going to do is study equations like this. Equations involving single derivatives. There's a set of techniques that you learn to do this, one of which is called separable equations, which many of you may have seen before in earlier classes. Probably not, because your teachers just ripped through that. So we'll do that in detail. The other method is called the method of integrating factors, which is going to involve integrating. I know that maybe that comes as a shock, but there's a lot of integrating in this class. A lot of it. So the book is going to do stuff to you where it's going to say things like, oh, as I go through this example, remember that the integral of x e to the x dx, it doesn't even say, it just writes down x e to the x minus e to the x plus c. It doesn't even like go out of its way to say anything about how to do that. It just writes it. So you're being trusted with those sorts of techniques. Yeah, so that's kind of the backdrop here. This idea of taking physical things and translating them into differential equations is like the massive change that happened to the way that science and engineering was done over the last like 300 years, right? Like almost everything that's written down is written down in terms of differential equations. Now, you might ask on the basis of this picture, okay, wow, that's some intense erasing. So that got a lot stronger over the last couple of quarters. So you might ask, if all we're studying is differential equations, I don't see any linear algebra in this. There's no linear algebra present in anything that we've written down here. Where's the linear algebra going to come from? So let me give you a couple examples of what happens next. So there's two ways that we could generalize the sort of thing we're doing here. The first is I could write an equation down with more derivatives in it. This is called a second order equation because it has two derivatives. And here, the general solution looks like this. Two unknowns. Anything of this form for any two arbitrary constants will satisfy this differential equation. You could verify that if you like. And the idea is, how do I know? I claim that this is all the solutions. Every solution to this differential equation is a combination of cosine of 2x and sine of 2x, multiplied by some constants. Why should you believe me? How do you know that if you're doing this for yourself and you write down a proposed solution that you've actually described all of the possible solutions? So this is a question about what's an idea called linear dependence or linear independence, and that is an idea of linear algebra. So the first application of linear algebra will be to study solutions to more complicated equations. The second is, if I write down something like x of t is equal to a rabbit population, and then something that eats it, like, I don't know, y of t is equal to a fox population, and say the rabbits have a birth rate, but also a death rate. They have a birth rate, a natural death rate, but also they're being eaten by foxes. So the more foxes there are, the more rabbits get eaten. And the foxes have a birth rate that is dependent on how many rabbits are available. The more rabbits there are, the more foxes there are going to be, right? So this is the base model of predator-prey model that comes from biology. And predator-prey models are driven now not just by one differential equation, but two variables that are interacting with each other. So this is a system of differential equations. This is the land of matrices and vectors. Systems of differential equations. So essentially the structure of the course is going to be this. We are going to start by looking at equations like this. First order equations and how to solve them and how to interpret them. Then we go over here and ignore differential equations for a while and learn linear algebra, matrices, and vectors. And then once we do that, then we pivot back over to second order and systems of differential equations because we'll have the tool set to describe those. So the combination of the linear algebra and the sort of first order stuff is going to unlock what's happening over here. And these are much more realistic pictures of what people study. So for example, probably the single most important differential equation is this one. So that is the equation of a damped harmonic oscillator, mass spring system with a shock absorber. That is used to model an unbelievable amount of stuff in the real world. Circuit theory is all built off that equation. Mass spring systems are built off that equation. That equation is, in the land of circuits, instead of having a mass on a spring, well, the spring is a capacitor, which is throwing current back and forth. And the damper, instead of being like a physical object that's like a shock absorber that's making the spring lower in force, instead it's a resistor. So you can code all of circuit theory into this differential equation as well. So second order equations require second order techniques, so we have to go through this first in order to understand really what's going on in these cases. Okay, So, I haven't really told you how to do anything yet, but that's the big picture, right? 3 components of the course. First order theory, which is chapter 1, a whole lot of linear algebra, which is chapters 2, 3, and 4, and then we pivot back up into differential equations for higher order differential equations and systems for the end of the course. Okay, so before I go on to chapter 1.2, are there any questions about anything I've set up here so far? All right, so I will continue to try to do my best to link the linear algebra to the differential equations. All right, so now we are moving on to 1.2. I will point out that this term, what I've done is I've made at the bottom of the note sheets that I've made, I have put the homework exercises for that particular section down at the bottom, the sort of assigned and collected ones. I will put those, eventually I'll collect those up into the homework assignments as well, but for now they're attached to these notes. Yep.
Because right now it says something about like all weekend numbers.
Yeah, so I'm not going to make you do that. I'm going to tell you precisely what problems I want you to turn in.
Okay.
Yeah, I'm modeling the course off of somebody else's, and that's the way he's got it written. So I'm just going to tell you which problems I want to see.
Okay, so if you want to see what the homework is right now, go to the end of the
Yeah, for right now, go to there's at the bottom it says collected. It just has a list down there that says collected problems. Those are the ones I want you to actually turn in for that section.
Got it.
Okay, so we're going to begin with section 1.2. And 1.2 is sort of your introduction to the terminology of differential equations. It would be nice when it gets warmer and they turn the heat off. Sorry about all the hot it is in here. All right, so definition 1.1. So I'm gonna have definition numbers that refer to the way that I've got them written in my notes, not necessarily in the book. So a differential equation is an equation in an unknown y of x involving derivatives. So for example, I could have the equation y prime is equal to 2x. That's the differential equation. Y prime prime plus 2y prime, maybe let me put this one, plus 3y prime plus 2y is equal to 0. Or something like y double prime times y is equal to the cosine of x. All differential equations. So just any combination of functions where we've involved derivatives. And the unknown here, we're thinking about implicitly. There's a lot of implicit functions going on here. We're thinking about y as implicitly being a function of x in all of these contexts. So probably the most important kind of differential equations are called linear differential equations. So a linear differential equation this is another definition. Linear differential equation has the form, or can be put into the form, a0 of x yn plus a1 of x yn minus 1 out to a n of x y is equal to capital F of x. So some notational things to keep track of here. These are just functions of x, no y's. The coefficients now are functions of x. And when I write yn, this is the same notation we used when we did Taylor's theorem. So yn just means n derivatives of y. The reason that we do that is because writing this down is really dumb. Y prime 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 dot 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 prime, and I write n down here. That's like terrible notation. So that just means n derivatives. So when I look at my structure for linear differential equations and I come over here, I can classify what exactly it is that I'm looking at. So this guy, linear or nonlinear?
Linear.
Yeah. Everything with y's in it is on one side. Every term involving a derivative just has y to that power, and there's no product of derivatives running anywhere. It's like a polynomial in the derivatives of y, is one way of thinking about it. Okay? This one is linear. If you like, you can identify the pieces. A0 of x here is the function 1 because it's the coefficient of the y prime term. A1 of x is the coefficient of the y term, which is 0. Capital F of x is equal to 2x. Now I got a question in the last class. Why do we even care about a function being on the other side of this? Why just not have y's all mixed together? And I guess I should probably motivate that. Like, why do we have this f of x over here? So if we go back to the mass spring problem I had written before, ay prime plus by is equal to f of x versus y prime prime plus ay prime plus by is equal to 0. If you'll just take it as a given for a moment that these are equations that model oscillators, this would be an oscillator like I've got a spring and I pull it out and I let it go and it does not act on, nothing outside the system is acting on it. Right? If it's a damped system, this term is going to turn out to represent a shock absorber, the spring kind of oscillates and then stops. Right? It wiggles down to nothing and stops oscillating. So these are different than if I have a mass spring system and then I hook something else up to the mass, like a driver of some kind. So these terms are going to correspond to what are called forcing terms, external forces in the system. So we want to study both of these. Physical systems where there's not an external force and physical systems where there is an external force. And so having this extra function over here allows us to capture both of those cases. All right, how about this guy? Linear or nonlinear? That's a polynomial in derivatives. The functions here are functions of x. That's linear. Nothing multiplied, none of the derivatives are multiplied. How about this one? Okay, mathematicians are pretty predictable, right? Because what does it mean to be nonlinear? Not linear. So if an equation is not linear, we call it nonlinear. So this equation is a nonlinear equation. And the reason is I've multiplied y by its second derivative. So I've mixed the derivatives together in terms, and the linearity condition requires that the derivatives stand by themselves multiplied by functions of x. Just to give you an example that's got some x's in it, I'll write down a linear function that does have some x's inside. So I could write cosine of x, y prime, plus 1 over x squared plus 1y is equal to the tangent of x. As nasty as that looks, that is still a linear equation because I have a function of x times y prime plus another function of x times y is equal to a function of x. So this one is also linear. I want to point out, I'm just seeding the future here a little bit, that another way to think about linearity is like this. So here's a definition. A linear operator, there's a fancy word, is a function L of y, so it eats functions, that satisfies the following. L of ay1 plus by2 is equal to a times L of y1 plus b times L of y2. This is the way everybody wishes square roots worked. That you can just take the function and smash it into the individual pieces, right? You know two really important functions or actions on functions that already satisfy this rule. So when you learned your differential calculus, one of the first things you learned is that the derivative of AF plus bg is equal to a times the derivative of f plus b times the derivative of g. Differentiation is a linear operator. You can spread it out to the individual terms and factor out constants. Integration is linear because you can split this up. Integrals split across the terms of a function. Integration and differentiation are linear operators. It's one of the most important things about them that they satisfy this property. And the claim here is, another way of thinking about the fact that these things are linear is that this function right here, if I call that L of y, that function of y also satisfies that same condition. If I wrote down L of y, I'm tempted to just erase with the wrong side of that eraser. Yeah, but then to be on film, but I just said that was, it's making me, like, you know.
Just do it when you're not.
L of y, well now, but now you said that, and now that's on film, so. If L of y,
You'll never do it.
y prime, that's right, I never would. Y prime prime plus 3y prime plus 2y. So if I make the whole left-hand side of that into put all the y's on one side and call that a function, an operator, and I could just check to see, hey, is it the case that if I stuck in ay1 plus by2, if I stuck in a combination into this function in the same way I stuck it into the derivatives and the integrals, if I stuck a combination here like this, does it satisfy the same property? Oh, let's see. ay1 plus by2 prime prime plus 3 times ay1 plus by2 prime plus ay1 2 times ay1 plus by2. So I've evaluated the operator on that combination of functions. And if you go through the process of actually calculating those derivatives, I think what you'll find is that you're going to end up with a times y1 prime prime plus 3 times y1 prime plus 2y1 plus b times y2 prime prime plus 3y2 prime plus 2y2. So take the derivatives using derivative rules and spread everything out and then resort it so the y1s are together and the y2s are together. And this is a times L of y1 plus b times L of y2. So this is a much more abstract way of thinking about this. So if this is confusing and it's the first time you've ever seen this kind of idea, don't worry about it. We're not actually going to use this idea to prove things are linear. I'm just pointing out that these are where matrices come from. Linear operators are the operators that I can represent with matrices. So I want to point out that there is a matrix that describes what's happening right here. This function is linear because, or this differential equation is linear because it comes from a linear operator. Or if you like, it acts like the derivatives do. This one, on the other hand, it's probably an amusing exercise if you're bored already on day one of your third quarter. You could check that if I gave you the function L of y is equal to L y prime prime times y, that L of y1 plus y2 is definitely not equal to L of y1 plus L of y2. Calculate them both, it will be obvious that's not true. So that is nonlinear, and actually what screws it up is the fact there's this product in here. Foiling that happens. Okay, so in our drift through terminology here, so we've done linearity. Okay, next idea, order of a differential equation. Don't do it. All right, so the order of a differential equation. The order of a differential equation so this is another definition. In my notes it is definition, come on. 1.5 is the highest derivative that appears in the equation. So that is to say, this is order 1. This is order 2, or second order. And this is order 2. Even though these are multiplied together, the highest derivative that appears here is order 2. And the last sort of piece of terminology I want us to look at today is this. So here's another definition. A linear differential equation is homogeneous. And I know this is pronounced differently than the word homogeneous. I don't know why we decided to split those things for each other, but mathematicians say homogeneous and some other fields say homogeneous. A linear differential equation is homogeneous if capital F of x is the 0 function. So that is to say, the function that occurs on the right-hand side is 0. So over here, this is non-homogeneous because capital F of x is 2x. So example, y prime is equal to 2x is non-homogeneous. Y prime prime plus 3y prime plus 2y is equal to 0 is homogeneous. Okay, so essentially, where the course is going to begin.
What does it mean for function to be homogeneous? Like it's just that. Like there's nothing.
It literally just means, so that's a good question here. This is what I mean about forcing functions versus non-forced equations,
Okay.
right? So the way to think about this, if you're physically inclined, or you're thinking about applications, which is probably everybody taking this class cares about applications here. The idea is that if we write down a homogeneous equation, I'm thinking of something like, y prime, that equation I wrote there, y prime prime plus 3y prime plus 2y is equal to 0. I would call this unforced, which is to say no external forces. On the other hand, if I write down something like y prime is equal to 2x, hell, like we can write down gravity, right? Acceleration, or sorry, velocity prime is equal to negative 9.8. Right? This is non-homogeneous. There's something else, there's an external force acting on the system is the idea, right? So this is a forced equation because there's external forces. And the idea is we're going to learn two different sets of techniques. There's one set of techniques that we use to handle unforced situations, homogeneous equations, and a different set that we have to use when there's actually something over here. All right. Anything else that I want to get to today? Yeah. Okay. So I should talk about what it means to be a general solution versus a particular solution. So a general solution, this will be the last thing we do here. A general solution to a differential equation describes all possible solutions. So for example, here's a really easy differential equation. We can solve this one without any technique at all. Y prime is equal to, I don't know, how about 4x to the third. That's a differential equation. What is its solution?
Y equals x to the 4th plus c.
I could just integrate to get the answer. So that is the general solution because every possible solution to this differential equation is described here. There's an arbitrary constant. There's an arbitrary constant, but any solution to this differential equation must be of this form. So this is all the solutions. If also I give you an initial condition, if also I tell you, given an initial condition, suppose I told you that I want the solution so that y of 0 is equal to 1. Well, then you would take your general solution, y of x is equal to x to the 4th plus c, but I want y of 0 to be equal to 0 to the 4th plus c, but that's supposed to be equal to 1, so c must be equal to 1. This is called a particular solution. And that's a term of art, right? A particular solution is a specific solution that satisfies an initial value. So if I give you extra information, you can lock down what the plus c is, you've got a particular solution. So the big questions that we're going to deal with in the later part of the class, now that we've got some terminology. So when I wrote down earlier y prime prime plus 4y is equal to 0, and then I told you that the general solution was c1 cosine of 2x plus c2 sine of 2x, and I claim that's the general solution, I am claiming every possible solution to that differential equation looks like that. All of them. And you could tell me c1 and c2 if I gave you two additional pieces of information, initial position and initial velocity, for example. I could tell you what c1 and c2 were. But I'm making a big claim when I say that. Every possible solution to that differential equation looks like one of these. Not just that these all solve the equation, but any other solution must be of that form. That's a big claim. So the linear algebra part of the class is what is going to give us conditions to check, okay, we're going to learn a technique for generating these solutions, or these solutions. How do we know when we've done it that we've got every possible thing we were after? All right, so next time we are going to talk about how to look at solutions to differential equations if I don't actually know what the solutions are. Just what the differential equation itself tells us and how we can interpret what that equation says. And then we'll move into separable differential equations, which is the single easiest way to get off the ground. So your first set of probably the best way to approach this course this term is try to work on the exercises that I gave you after we talked about that section, just kind of a day at a time. I'll try to portion those things out. We're finished with what I want to say about 1.2 mostly, so go on and do 1.2. Homework will be collected on, I think I've got it set up for Tuesdays of the following week. And I know, office hours right now are Monday 2 to 4, Tuesday 2 to 3, Thursday 2 to 3. I know that doesn't work for everybody. I have time in the mornings as well, but I don't know yet. So if you have strong preferences about what mornings I can give you and when, send me an email and I'll put something in the morning as well. So you can. All right. Thanks for rejoining me. I'm excited to do this.